Welcome everyone to another Thursday seminar in computer engineering. Uh, we are already more than halfway our seminar classes. We started with internet architecture evolution, cloud gaming, quantum, uh, SDN to support large transfers. We have this also scheduled, and today I'm very glad to have Chrysa, a collaborator that is working on a very interesting EU project that is coming to an end after almost 3 years towards 6G. And also that our center, the Smartness Center, has since a couple of weeks one of our PhD students over there contributing, doing collaborative research towards 6G. And this is precisely the topic of Chrysa's today. What is going on in the design of a 6G system that, as everything these days, is AI native, AI capable, AI improved. Okay, I don't spend valuable time reading out the biographies of our seminar speakers. You can find, as always, their contact and Google Scholar information. What I can say, Chris, that I'm very happy, as not everyone knows, but my mother was born in Amsterdam, is Dutch, and that's why I selected today also the orange intrigue polo T-shirt in honor to the Netherlands and to Dutch, and I have also my water in orange, so it's very orangey today. Just to
I don't know if you speak in Netherlands. Netherlands.
speak Hollands. Een beetje.
Ambition. I don't speak yet, but hopefully next years.
I speak German, a little bit of every language, not even Spanish, fully fully fluent. Okay, so let me, with that introduction, stop my sharing and invite you to share your screen, and then I will pass you.
I think. I think you can see my screen, right? So I'm putting this into, yeah.
Yeah. It's
Let me know when can we start. Yeah?
Yeah, the floor is yours, and
Thanks.
in around 40 minutes.
Okay. First of all, Christian, thank you very much for the invitation. It's my pleasure. I mean, we had arranged it also from last year on, but we didn't manage to make it happen. So I'm very happy to be here today with you guys virtually. Hopefully, in the next years, somehow I'll make my way to Brazil. So let me first say a few things about myself, and I will try to give you also a bit of an introduction onto the topic that I'm trying to address today. We're going to try to see what is an AI native 6G system architecture is in the next 40 minutes. So a few things about myself. I'm an associate professor at the University of Amsterdam at the Informatics Institute, Computer Science, and I work in a group called Multiscale Network Systems, and particularly the networking people is me, Paola Grosso, and Mario Xavieres. We're basically collaborating, working together in a number of different projects and initiatives with regards to mobile networks, programmability, controllability of the networks, and network automation. Of course, multi-scale network systems is a bigger group. It also has aspects, looking into aspects into quantum network control or high-performance computing and whatnot. But I'm focusing a little bit on the work that we are doing, okay, as networking people. So, starting a little bit, I know that most of you guys have, or many of you have already, mobile networks as users already. All right. So essentially, most of you are already connecting wirelessly to the networks, and the networks, because of the increase in users, they should become, and they must become, more autonomous and more adaptable in order to be able to support new services and meet the changing needs that are coming from you guys as users, and of course businesses. And this figure here is the standard figure of the XG evolution, let's say, where essentially each generation, what does it provide us? Basically, it achieves larger bandwidths, higher data rates, better quality of service, leading essentially to richer services, which means, as you see here, our goal is to go into a fully connected world with 6G, with a number of additional, let's say, services on top of what 5G provided. Looking back a little bit into the evolution, let's say, from the previous generation, 5G was very important. Why? Because essentially it marked a paradigm shift for the telecommunication industry, in the sense of it provided added value services to vertical industries, so healthcare, automotive, and whatnot. So basically, a set of different use cases came into the picture, okay, with diverse service requirements, not just mobile broadband, as in the case of 4G. And these were basically categorized into three core categories. Enhanced mobile broadband, that refers to, let's say, it's the standard more broadband communication, but with better quality of service KPIs than the 4G communication. Ultra reliable latency communication for applications targeting, as it says, better reliability and lower latency for more, let's say, mission critical applications like industrial, IoT, gaming, and so on and so forth. And massive machine type communications to support a massive numbers of connected devices, looking into use cases like IoT and smart cities. So this was, let's say, the goal for 5G. Okay, this was the difference. But of course, it was made evident throughout this period of research and pre-standardization and standardization that the on-size fits all model that we had in networking until that time was no longer basically capable of supporting the diverse requirements that we had for the different verticals, vertical industries, as I said, healthcare, automation, industrial automation, and whatnot, and the corresponding applications. And in that context, network slicing emerged as a very critical feature for mobile networks. Essentially, what is network slicing is it enables the coexistence of multiple and mutually isolated end-to-end logical networks composed by a number of customizable, basically, software-defined functions that are tailored to a given application or service. And in that sense, it relies on a number of technologies. Of course, it requires technologies like network functions virtualization, software-defined networking, cloud computing, network virtualization, and whatnot. So essentially, this multiplicity of the advancements that were made in these underlying technologies led to the emergence of a network slicing as a key feature for mobile networks. And it allowed us to provide optimized network service delivery for all these heterogeneous, let's say, use cases that were envisioned in 5G. However, it was made evident with the initial rollout that essentially 5G systems are falling short on meeting the basic performance requirements for cases like real-time mission-critical applications, such as, for example, manufacturing processes, or in some cases AGVs, that could require either lower latency or higher reliability than what is offered in 5G. So 6G basically is emerging, on one hand, to bridge this gap and meet the needs for future existing services that were not necessarily covered with 5G, as well as future services, which will be centered, as we expect, around data-driven, intelligent, and automated processes. So what we see here is basically an overview of the families, use case families that are provided here in the circles. These are described by the European Union, the Smart Networks and Services group initiative that essentially brings together the consolidated view of the European research projects on 6G. And this view was also presented in the 3GPP workshop on the 6G use cases. back in 2023. So we see a number of different additional to existing ones, because immersive experience, we're already like looking into AV, augmented reality or virtual reality applications, but we're looking into also aspects of collaborative robots, the use of digital twins, or composable digital twins of the physical world. So these are new use cases that are popping up, essentially, that are envisioned in 6G, and the requirements of which we should be able to support with the telecommunication infrastructure and the network services that we deploy. Now, to support these use case families, essentially, ITU has approved a release, again in 2023, the IMT, the International Mobile Telecommunications Vision for 2030, okay, which guides the development of 6G networks. And as you see on the left-hand side here, in this framework, we have a number of, for example, we have applications are extended, the use case and groups that we have previously, which was essentially EMBB, URLLC, and massive machine-type communications, are now extended to immersive communications, hyper-reliable and low-latency communications, and massive communications. Okay, while we also have new ones, like, for example, integrated sensing and communication, JSAC or ISAC, that facilitates essentially applications that require sensing capabilities with the same infrastructure, with just using the radio infrastructure. So you have this, let's say, new user scenarios that are visioned by IMT 2030, and on the right-hand side, you see the corresponding capabilities that are expected to meet. So enhanced capabilities that are expected for IMT 2030 in terms of security, reliability, and whatnot. For example, we go to sub-millisecond latency, right? Or terabyte, or increased, let's say, big data rates. And also additional new capabilities like sustainability, interoperability, and whatnot. So these targets and this range of values are essentially given the capabilities that are estimated, that are the targets for us, for our research and investigation, in order to address and create, let's say, the next generation of mobile networks. And to deliver these capabilities for 6G, we basically need a number of enhancements for existing technologies, that, like, for example, the radio interface, signal processing, and whatnot, as well as investigate new technologies, like, for example, with the immersion of the digital twins of the network and whatnot. And this is an overview that is provided in the white paper that was again issued like a few months ago from the European, from the 6G Infrastructure Association. And it's about the European vision for the 6G network ecosystem. It's an interesting, it is an interesting read. So a subset of these technologies are essentially the content of the research at the MNS group, and cover, of course, the ongoing and research work and the work that we're doing within the context of this RS6G, of the European project that I'm coordinating. So today, I want to talk in particular about network intelligence, which is essentially refers to the integration of AI, of machine learning, AI and machine learning technologies through the network's design, deployment, and operation, and enabling essentially automation at all network levels. And whereas topics like zero-touch management and edge intelligence were already introduced in 5G, zero-touch management essentially refers to a fully automated network and network service lifecycle management and the corresponding operations, so deployment, operation, configuration, monitoring, and whatnot, without the need for a human in the loop, essentially. Or edge intelligence, that was essentially the integration of data processing and AI capabilities at the edge of the network, closer to the end users. So these lead, essentially, these were, although these were already introduced in 5G, now we're moving towards also an AI native 6G architecture, so which is a concept that is highly integrated as a view, is a vision for 6G. But what does that mean? That is a question, actually, that we'll try to briefly introduce. what is the concept and the principles for AI native architecture in the telecom context, and see as a case study Desire 6C, which is essentially was essentially designed, written and designed to pursue this goal. We're gonna then, as a second step, depending also on the time, we're gonna look into a number of specific problems that are related to network automation and how machine learning can be used to support these operations. And it's a number of problems like SLA decomposition, resource allocation, or aspects of service assurance. And then I'm just gonna briefly say what we're doing as a continuation, let's say, of Desire 6C. Okay. So let's try to set, let's say, the basis of what is AI native in the telecom context. So essentially, this is based, the figure on the left is based on a very interesting white paper that was released by Ericsson back in 2023. So what is AI native for a network system? It essentially goes beyond simply using machine learning in parts of the system, or further away from what was envisioned in 5G, where essentially AI was an afterthought, was a component that you could actually ask or get information and then send back to and use in your system. So in the sense, AI native is having intrinsic trustworthy AI capabilities in the system, and AI is a natural part of the functionality in terms of design, deployment, operation, and maintenance. So an AI native implementation essentially is managed by AI-aware components, and it includes functionality for managing also the life cycle of AI-based components. So what does that mean? So first of all, what are the principles? The purpose of the AI native system is to achieve any of its objectives using AI-assisted and data-driven approaches. So in our case, for example, you will see that our goal is to use AI to enable zero-touch operation of the 6G system, and also to support functional and non-functional optimizations. An AI network must be perceptive, which means essentially that it must be aware of its environment and the changes that are happening to its environment in order to use it to support AI-based functionality, updating the models and whatnot. And this goes to the next step, which is, it means that the system should also be cognitive. It means that it should learn from its own experience and evolve its strategies to fulfill high-level intents that are coming, let's say, that are related to what the tenants are instructing or are requiring, or what the network service requires from with regards to its operation. So another property, the system, the native system should be interactive in that sense. It should be able to support the lifecycle management of any AI-based functionality, and at the same time, to be able to generate and expose data and knowledge in a way that is easy to be consumed by the system or also external applications and services. And of course, it must ensure that trustworthiness, fairness, privacy, and explainability and collaborative intelligence across distributed agents. And what does explainability means? Understanding that how a machine learning model makes decisions, while fairness ensures that those decisions are made impartially and without bias, whereas trustworthiness means that is a more generic term that refers to the degree to which users can rely on the AI system to behave as intended. So what would be the outcome of this let's say system? Essentially a network system that supports, as I said, zero-touch automation. This is our goal, which is a key vision for 6G. Now, the idea, of course, is that network intelligence, and when I mean network intelligence, I mean the capability of the system to autonomously operate is pervasive, enabling autonomous lifecycle management of services and infrastructure with minimal human intervention. Now, the question is, how we can use, how is this related to Desire6Z? So in Desire6Z in particular, what we try to do is to adopt this model, these principles, and go a step further in the sense that we are combining AI native capabilities or an AI native approach with full programmability of the network. And in that sense, it allows an AI native approach for the network, because you can you have more flexibility, more degrees of freedom in how you program and configure your network. So we look at, so these are, let's say, I would say that these are the main points: full programmability from the control down to the data plane, and AI native approach for the network, along with a number of different innovations that I will try to mention a little bit. And all this let's say, set is supposed to support scalable and autonomic behavior. So I will start with Desire6Z, and then in the future work, I will say a few things about FNS and the differentiator, the other AI native, let's say, system architecture, which goes a little bit further than Desire6Z. So what was... So what is the scope, basically? Sorry, first let me go to this one. So Desire6Z is the name of a project called Deprogrammability and Secure Distributed Intelligence for Real-Time End-to-End Networks, with a number of different partners and 3-year duration of 3 years. Now, the scope of the project is essentially to design and develop a zero-touch control management and orchestration platform with native integration of AI to support extreme application requirements. We're talking about real-time mission-critical applications, so ideally sub-millisecond delay, higher reliability, and whatnot. And this should happen over a performant, measurable, and programmable data plane. So also at the time where Desire6Z, let's say, was we kick off Desire6Z, there was a number of different projects, also initiatives in the EU, that were looking at the same capabilities from a more deterministic point of view, with TSN and .NET. So we thought, can we achieve the same extreme KPIs with just exploiting the full programmability of the network? That was one of the, let's say, ideas, along with machine learning approaches for making the network autonomous. So to that end, we are looking at 2 representative 6Z use cases. One is augmented reality and the digital twin, both in the context of industrial applications. Okay, and in that sense, we are targeting, as I said, specific KPIs with experiments that are taking place either in lab environments or in field environments. So in one case, we have the 5-tonic. It's in the case of the digital twin of the robotic dog that you see here, is a testbed that is, we're using the 5-tonic testbed in Madrid, where essentially we're integrating, as the project continues, we're integrating a Desire6Z domain with a deterministic domain to provide end-to-end service. Okay, so let me, so how we try to achieve this data-driven autonomous networking? So we're basically focusing in Desire6Z on different aspects of, as you see here, the orchestration, management, control, and data plane. So we're kind of looking at it from in a kind of vertical point of view, okay? So a key innovation that, as I said, we consider is data plane programmability end-to-end. The goal is to support multi-tenancy at the data plane, cloud-native properties, again at the data plane, and flexible functional floating, so that you can, let's say, seamlessly use the network cloud continuum. An important part, as you see also for the AI native approach, is the fact that we are looking into pervasive monitoring system and how this can be created exploiting data plane programmability. The architecture that we're proposing is cloud native and serverless, with dynamic deployment of services across the edge cloud continuum using different hardware components, different independently of the hardware. And intelligence, in our case, is distributed with the use of the multi-agent systems, by using multi-agent systems that push decision-making closer to the data plane, and the use of a service management and orchestration plane, which is a more, let's say, centralized approach. And finally, what we what we do is we embed distributed ledger technology, DLT, for zero trust security. We're using essentially to enable domain federation, and also to enable the trust management security aspects between the different intelligence agents as they're collaborating, as they're communicating with each other. So how does this reflect an AI-native system architecture, right? So that's the first question. Okay, so let me go like this. In our case, to make the system perspective, in Desire 6Z, we, as I said, we introduce a pervasive monitoring system that stretches up to the user equipment, to the UE, utilizing in that sense, network telemetry solutions, programmable network telemetry solutions that enable accurate, real-time, end-to-end information collection. And this information is, of course, used to, the idea is to have this capability to produce different levels of data, different volumes of data that would help your algorithms, your machine learning approaches work. We also employ an AI-driven service management and orchestration layer that supports any non-real-time, let's say, decision-making over one second in terms of time frame, and any kind of optimizations, as well as the lifecycle management of the machine learning pipelines themselves that are deployed on the system, like, for example, the agents, right? And as I said, we use a multi-agent system. We support the idea with the masses to, let's say, enable near real-time control loops, since the agents are interoperating, pushing network intelligence in that sense closer to the data plane. So avoiding the need to go up to the SMO in order to reduce complexity, enhance scalability of the system and whatnot. And our work, our investigations also, our research also includes edge AI related to the network service or the applications. Like, for example, you see here, we're looking to federated learning for the configuration of reflective intelligence services, or we're looking to third-party applications enabled by the system. So we're trying to see it from a kind of holistic perspective, as I said. And finally, we're looking into in-network machine learning and frameworks that essentially enable fast cross-framework and cross-hardware execution of AI, of the AI workloads themselves, right? So this is the more work that is pertaining to companies like NEC or other companies that are using, that are working on this direction. So in that sense, we consider that AI is pervasive, right? And Desire 6Z, its goal is to enable collaborative intelligence across across a network, across different technology domains. So, what is the goal of the MNS? I will try, based on this, let's say, introduction about the Desire 6Z, this description of the Desire 6Z architecture, I will try to give you a little bit of an overview of what are the problems that we are dealing with in terms of research, okay, in terms of what are the PhD students are working on. So we're looking into aspects, in particular, we're looking into aspects of network automation. So what does that mean? So here you see it's a simplified version of the previous architecture, of the Desire 6Z architecture. You have the service management and orchestration layer, you have the individual domain controllers, like if it's radio, the near real-time RIC can be an SDN controller, or it can be the infrastructure management layer that uses Kubernetes as a computing controller, and the multi-agent system that should be used for decision making, for intelligent decision making. Now, the question that we have is, how can a network slice in this kind of architecture can be instantiated, first of all, over the network of the telco operator, of the telco? And the second question is how we can maintain, first of all, how we can efficiently deploy the network service, and how we can maintain the KPIs that we have agreed for the particular service, okay, which is about essentially service, we call it service assurance. So consider this case here. On the left-hand side, you have a user that, in a very basic, let's say, approach, you have a user that triggers a service request. Now, the service request, in this case, we we illustrate it as a service function chain, which is essentially an ordered sequence of network functions. I don't know, firewalls, load balancers, mobile network functions, and whatnot. And these functions, data must flow through these functions, must pass through these functions from the source to the destination. So this is a service function chain. And the service function chain from the user comes, we assume that it comes with an SLA, with a service level agreement, which is a formal contract between the service provider and the customer and the user that defines the expected level of service performance. You agree upon specific KPIs, like, for example, throughput in terms of delay, reliability, and whatnot. All right, so first, what it happens is that the user triggers a service request, and the request should be sent to the operator with its associated end-to-end SLA. We assume that the orchestrator receives the request, and it will decompose the corresponding end-to-end service level agreement into partial service level agreements for each of the domains according to the available resources or information that it has available. For example, if you have, for example, an end-to-end delay for a particular service agreed upon, the orchestrator should define the corresponding delay budgets per domain, radio, transport, for example, in core, and based on that, it decompose accordingly the problem, partitioning apart from setting up the delay budget per domain, decomposing also partitioning the network service graph that we have here, the service function chain, to the corresponding partial SFCs that will be sent to its domain to be deployed. So this is, let's say, so the part of the designing the delay budgets, let's call it SLA decomposition. Now, assuming that we have also partitioned the graph, the service function chain, then each of these individual partial SFCs should be actually embedded, should be mapped into the underlying domains. And this is a part of which is called SFC embedding, the problem that is called service function chain embedding, which means basically that as soon as we embed them and we map them and we deploy them, then essentially we interconnect them, then essentially we have the deployment of the network service. Now, this third part is about, okay, service assurance. What does that mean? So as your network operates, due to the, first of all, of the dynamicity on one hand of the network traffic from the network service itself, as well as the availability of the resources in the different domains, you need to be able at every time to meet the grid SLA, which means that you need to probably scale up and down the allocated resources accordingly. So this reflects to service elasticity, how I adjust my resources, which means that I need to, could be, for example, I need to scale out functions, or I need to migrate to a different resource so that I make sure that the partial SLAs are met. So this reflects to us, the problem is called service elasticity. Now, these all three topics are what we call part of automation for network slice lifecycle management, because it reflects service deployment and service assurance. And the goal of our research, let's say, also in this RSXE, is to introduce, to see how machine learning approaches-based solutions can solve these corresponding problems. So in the first case, let's have a look at the SLA decomposition. We're basically, I won't go into all of the problems. I'll just give you an overview of a couple just to get an idea of what we're trying to address. So the SLA decomposition, imagine that we have essentially, we model the SLA for a particular network service as a vector of bounds for the performance metrics, like, for example, the end-to-end delay, the end-to-end bandwidth, and reliability. We assume now that the orchestrator, the service management and orchestration layer, has no knowledge. In our case, we assume that it has no knowledge of the state of the underlying domains, and that the only data, so I don't know what resources are available, the only data that are available to me is admission control feedback from each of the domains from the prior requests, okay? So whether or not previous requests, service requests, were actually accepted by the domain controllers. So based on this data, what we want to do is we want the orchestrator, based on this information, we want the orchestrator to construct a corresponding risk model per domain and use that model to decompose the SLA. So this is, let's say, our goal with limited information to be able to identify how we can split the SLA between the different network domains. And what is this model? This risk model is essentially, it maps this partial SLA to acceptance probabilities for the domain. Okay, so based on this, we can use all the risk models and some optimization approach to decompose the corresponding SLA. So in our previous work, what we did is we created a very parameter-free, let's say, risk model per domain that relies on such observed data on admission control. And because that, as you see on the left-hand side here, it was basically involved in maximizing the likelihood of observed admission control decisions over the SLA request, considering always that we have a monotonicity constraint, which means that the stricter the SLA, the more difficult it will be accepted, basically. Okay, so because this problem is basically non-linear, although it was effective, it has many limitations. It's computationally expensive, it lacks flexibility, it cannot capture any nonlinear relationships or data variability, especially when we're going to larger scale. So although useful and effective, it is restrictive in many senses. So what was our, so then the thing is, it was, okay, let's try to see if we can employ neural network-based risk models to model the domain behavior, as essentially with a neural network, it would allow for greater flexibility, greater accuracy in that sense, and also scale. So our goal in that sense was, let's try to model the corresponding probability with a neural network, acceptance probability per domain with a neural network, and then use this to decompose the end-to-end SLA. Again, the trick or the difference, let's say, to this was the fact that we had, again, to consider this monotonic property. So we have to, as you see here in the first, we have to consider this partial order relation that a less strict SLA has higher chance to be accepted, always, okay? And this property led us to consider monotonic neural networks. And as soon as we devise this, the goal is to find an optimal decomposition. So as you see here, so that the global acceptance probability of the service level agreement is essentially maximized, assuming all the different domains like transport, core, or radio make the decisions independently. So I won't go into the details. I'm just going to say that we evaluated a number of different neural networks. We tried to investigate these monotonic properties for the neural networks, and we compared them with a basic baseline vanilla neural network. And indicatively, you see here, these contours, for example, indicate the acceptance probability from 0 to maximum, right? Depending on the different SLAs, throughput and corresponding delay. It's on a per domain basis. And this is the corresponding approximations with our neural network-based risk model, or with the initial, our first approach on a parameter-free risk model. And in general, we saw what we identified is even with a smaller, very small set of samples, we managed to get quite efficient, quite well contour plots, and to model the behavior effectively. And as the number of, let's say, these admission control points information increases, then we also increase the acceptance probability, the end-to-end acceptance probability for the entire SLA, which means that the service request, the delay budgets, or the corresponding throughput that is required can be supported effectively by the underlying domains. And this led to a number of different problems. Okay, how these are risk models are, let's say, static. Can we make them dynamic? That was our second approach. So, and so on and so forth. All right, so fine up to here. We have done the service, the SLA decomposition. How do we embed? We have now a partial, assuming that we get also a partial graph, which was not investigated in the previous problem. How can we embed this graph? how we can embed this partial service request to the underlying domain. This is a so-called service function chain embedding problem, or VNF forwarding graph embedding problem, where essentially, as you see here, what we're trying to do is to get to place the VNFs to a corresponding computing infrastructure, okay, and to steer the traffic between them as it is defined, as it is, let's say, dictated by the service graph. Of course, we need to take into account that the resources allocated on the physical nodes and links should not exceed the respective residual capacities. Okay, now these decisions, although you could say these are disjoint decisions, and you decouple, you can place the functions and then interconnect them. They are actually interrelated, because the further away you essentially place the VNFs, the more longer is the path that you essentially need to use in order to interconnect them, which has an impact on the bandwidth use, it has an impact on cost, and it has an impact on, could be on delay, and so on and so forth. So that is a joint problem that it's a very well-known problem in literature, of course, and there has been, for many years, traditional optimization approaches, heuristics or meta-heuristics or approximations have been used to address it. However, such solutions, first of all, especially if we're talking about exact solutions, do not scale. And they're also suboptimal in the long run, because at every case, you're looking into a snapshot of the network state at the time when you're actually doing the mapping. So you have to think about what will happen in the future. This leads to a fragmentation of resources in the future, because of the fact that service requests are coming and going. They're not there for you consider that they have a specific duration. Okay, so what did we do in the most in general, what was the state of the art about this problem was essentially we're trying to address the service function chain embedding problem with reinforcement learning, with machine learning. Why? Because it is a very good, it is very effective for nudging essentially the decision-making process in the right direction in an environment where resource demands and supply availability of resources is uncertain. However, at most of the solutions at the time were proceeding to map the VNFs sequentially, one by one. Okay, like first the first one, the second one, and whatnot. Okay, why? In order to avoid problems in scalability, in exploring essentially in dimensionality of the problem. So in our case, what we said, okay, let's see if we can. We tried to investigate the use, how we can make this a single step, using reinforcement learning and different approaches like Q-learning or deep Q-learning, but at a single step. First of all, we thought that it is unrealistic to assume that we will have access to the entire state of the problem. So in that sense, we model it as a partially observable MTP, and then we use compute capacity per node and the average residual lifetime of the request allocated to the node. And what we do actually is we don't use Q-learning or deep Q-learning to do the mapping, but we use it to do admission control, and we use simple approaches for the like greedy placement and linear programming we use for virtual embedding. So in that sense, we're transforming the problem, but it shows that it has quite good results compared to the mixed integer, to the optimal approach that converges to, as you see here, for example, converges to a rejection ratio, rejection in terms of how many requests are accepted to the system, of 60%, whereas in the case of reinforcement learning, you have a rejection ratio of approximately 40% with violation ratio in terms of the SLA of less than 10%. So there is a trade-off, but it's an interesting thing to see that this is generally a solution that in the long run, it seems to be better also in terms of fragmentation of resources. So I will not go into this because we're almost at the 40 minutes. We're at the 40 minutes. I will not go into this problem about service elasticity. I just wanted to say this is a number of papers basically in the work that we have done in this area. Now, our next goal with regards to AI native an AI native 6G system and the corresponding approaches basically for AI-driven network automation, all fall within the context of the Future Network Services Project, which is the flagship initiative for 6G in the Netherlands. It has started last year and will run until 2030, basically with the initial rollout of the 6G services, of the 6G networks. And there, I just want to go here and show that to you guys that what we're looking on, we're going a step further. And apart from whatever we call as a native network automation with intelligence, you see the individual brains at every aspect, let's say, of the architecture, we're also looking on how the digital twin of the network can assist in this process. So modeling, first of all, the creation and architecture of the digital twin and how it can assist network automation. And also we're pushing from, let's say, whereas in Desire CG, we're working mostly on the service management and orchestration and let's say the multi-agent system, we're trying to push a little bit towards the data plane and look into aspects of in-network machine learning for real-time control. So this is the aspects of my work. I just put here for reference the group, which is a number of PhD students and a single postdoc at the time, Anestis. So we're looking, as you see, we're looking into different aspects that reflect all this effort, from machine learning for network slice management to AI-driven, AI-assisted in-band network telemetry to data plane programmability that will allows for flexibility in reprogramming and reprogramming your network. So that is all from my side. I think I'm almost time. Yeah, a bit over time.
Thanks, Chrysa. Lots of content. I mean, there is
Lots
a lot of.
Yes, I know. But I wanted to give also an overview of the problems apart from the AI nativeness. Let's say, architecture-wise, what are the problems that people should are looking into? Yeah.
Yes, nice. Thank you a lot. Thank you a lot. It was, I must confess, there were a few papers that I was not aware of this SCLA decomposition, something that we were also working in some years ago. But let's see, let's make most out of these 10 minutes that we have. I was going through you can stop sharing now if you want.
Yes.
I was going through the questions of our students, and there are a few good ones. There is already one in the chat of our YouTube streaming by Marcos Lima Romero, and he asks about this very recent topic or very active topic of agentic AIs. You have agents in and you had agents many years ago, because remember that these projects were proposed and written like 4 years ago.
Yeah.
And he asks, how do you see the impact of LLM-based agents and agentic AI workflows within these AI native 6G networks?
Well, this is a very active topic of research for us. I didn't go into this because I tried to present this RCC, but this is the next step. Essentially, we're looking into how, LLMs from one side, even from for intent translation, or using LLMs for goals or goal-oriented communication between the different agents. So there are it spans many different aspects. In my opinion, in that area, in the area of service management and orchestration. So it is a very active topic of research, and it will be in my opinion, it will play a pivotal role in the next, let's say, round of research projects in the area.
Yeah. I've seen also some recent research, open source research by Cisco in this Internet of Agents. So good. Now this is the
thing is, the interesting thing is that we started already in Desire 65 years ago, basically with the agent-based approach for network automation, and this is that you see that the direction is that way, and goes, but a bit more complex than what we have in Desire 60 with a larger number of agents, also at the orchestration level or at lower levels.
Nice. Yeah. Okay, so this is the spreadsheet that I mentioned that our students do their homework. So they have been identifying related work, and
Yes.
they prepare also some questions. So I've selected just a few. Of course, I can share with you because this is always interesting to see. This is one that we have common together. You know, smartness is a industry, academic, and government initiative. The EU projects are also these public-private partnerships. So there is money from companies, money from academia. The question is rather generic, right? So uh, uh, how uh, how do you see this collaboration? Let's maybe if we can rephrase. What do you think could be done further? Because these programs like FAPES, the Engineering Research Centers of Smartness, or the EU SNS, they are successful. They show this, but uh, there are always things that could be improved, and there are more and more opportunities that are not explored. Given your extensive experience, as the student says, in both the academic and the industrial, what do you have in your head that
Well,
could be done?
what I
That,
would want, particularly myself, also going from, let's say, Nokia Bell Labs to the academia, given both experiences, I would like to see a more close collaboration between let's say industrial researchers and the university, because even at this, I mean, it depends a lot on the team, the industrial team that is working, the team from the industry that is working, but I don't see, I mean, in Europe, it's a very much restricted to the cases where funding is available through the EU. I would, which is, not ideal. I would expect to see something more closely to what has taking place in the US in that area. In that,
I'm not very familiar about the US funding, but I can tell that in Brazil we have this innovation law where the companies can directly invest money into industry, into collaborations with academia, and then they can use at the end of the year with the tax money they can get it back. And this has been working, and it's also at the roots of many of our collaborations, for instance with Ericsson for over 25 years. So I can see your points, like this more direct flow between the companies and the academics that have a
exactly.
good match, and it's a win-win, and you don't need to go over the hard or overhead process of you and building all
There
these
is a hard
large.
process of the European projects, of the research projects, and most of the funding is done like, I mean, most of the collaborations are done in this way. And I've been working in different universities also in Europe.
Mhm.
And that is the case, or that is the modus operandi, let's say, for research. I would like to see in, like also fund, but the industry also supporting, let's say, research in the academia in that sense. Could be with equipment, could be with collaboration, with in kind or in cash, I don't know. But it's not something that is very, like straightforward or very easy to be done in Europe.
Good data. I mean, if you don't have valuable large data sets, you cannot do meaningful research, right?
Yes, that's true. That is also something not available, even
AI,
in of projects.
AI native without good data or with
Yeah, well,
it's.
exactly. No, exactly. The problem is, in that sense, we're kind of trying to exploit whatever we have and whatever synthetic data we can produce ourselves, which is
Mhm.
not by far not what we want.
Yeah.
I know there are cases. It also depends on the university, or it depends on the academic partner. There are people that have established relations with the industry, so it depends a bit. But I
Mhm.
would like a bit more effort in that sense from the industry towards academia, more support.
Of course, they want to see the outcome, and that it pays off. And yeah, this data augmentation is another topic that we are doing some stuff now with KTH, with one PhD student over there as well. So there is there are avenues there to overcome the lack of
Yes,
data.
yes. We also do some work on data augmentation, basically with transformer models. That is another topic, let's say, of research, which is not mentioned here. It's not in. It's in the context of FNS, but that is another topic. Yeah, another direction we're looking into.
Good, good. And we have one PhD student abroad in KTH this year, so let's do something. And, and this question that I just picked up goes directly or touches this aspect. Okay, look, this is a smart one. So it says like the network's AI agents can reconfigure resources on the fly. What
Yeah,
has been the toughest explainability? You know, this comes in every review paper.
yeah.
The you have
Well, first of
operate.
all, first of all, that is a very good question. Okay, but this is not a question that I can because I'm not. I still. I mean, not looking. I haven't looked deep into the explainability aspect, so I'm not sure that I can answer this question actually. But this is an
Mhm.
interesting one. So our goal,
This is
for example,
a
so
review
for
question.
example, is to see also aspects of explainability, why the network changes, why a decision is made, and how it is made and why it is made. But this is aspects for future research for us.
Okay. This one, oh, I think you already touched. I had selected that, but I mean, these R6G is natively distributed, right?
Correct.
So this student was picking up this question, how to balance between centralized cloud and distributed in terms of latency and resource. I mean, this
But
is
yeah, this is also a nice question. The idea is that essentially that every operation that is related to every functionality, AI-driven functionality that is related to the service operation is distributed, so lower latency, better performance. And it could be you're also looking at different trade-offs, different models, depending on where you apply it. Whereas when we're talking about more centralized approaches, we're looking into more on the service deployment level, where essentially you're making a decision about how you initially deploy your network service.
Mhm. Well, yeah, there was one question regarding this timeliness on the different, vastly different time scales of AI-driven inference at the edge and slower reconfiguration. This student probably works on optical transfer hardware because of the question. This was not green. That means I just selected it. Okay, we have over 40 students. I'm very glad about this seminar. It's I joke that it's one of my best hours in the week because I catch up with people, collaborators like you. We have some 10, 15-minute chat. We have some briefing, but none of the questions were prepared, right? Nothing about the talk was faked, and I really enjoyed
Yeah, that's
this
true. That is
seminar.
also a very interesting and very good question. How do you reconcile the vastly different time scales? Where essentially you kind of, how can I say this, separate responsibilities, right? Separation of responsibilities. So essentially whatever cannot be solved at the lower level where you kind of have faster shorter control loops and faster time scales, you basically push it to the upper layers when you have longer time scales and different, let's say, more heavy machine learning models. So it's a matter of how you decide, when you decide that you cannot solve a problem at fast and in a fast and more efficient manner at closer to the data plane. In this axis, that is the goal.
Right. Separation of concerns. And we need to separate concerns because students at 2 p.m., many of them they have their afternoon classes. We are right. We use this lunchtime for these seminars where it's a good EU time, good US time, good lunchtime over here in Brazil. And it will be a great time catching up further in the upcoming EU events that we know that will be meeting, and it's great. Again, thank you for your time and the
Thank you for the
program.
guys. Thank you for the invitation. Everybody, if anybody wants, they can contact me through my email. I would be glad to also discuss any topics or additional questions. If you can provide me with the questions, Christian, that the guys
That's
asked.
that's done. Okay, thank you, and stay tuned for the next seminars.
Take
Bye
care,
bye.
guys.